we'll start with regulation of enzyme activity, and one of the things that we might want to discuss first is why do we need to regulate enzyme activity at all before we try and understand how we do that. And the way and some of the reasons that we might want to regulate enzyme activity are things that I talked about in the first lecture, which is that these enzymes are essentially used in the biological pathways in very trace quantities, and they are specific, right? So the enzymes by definition are specific. So because of specificity and because of the fact that they are used typically in very minute quantities, regulation is important. And I'll list for you the reasons for regulation. So first, the need for inhibition is to control the amount of product formed by the reaction. Okay, so that's the first need for inhibition, to control the amount of product formed by the reaction. So you don't want a lot of the product formed. The reason is that a certain product in a biological pathway has a certain activity, and you want a specific amount of product to attain that activity, not less, not more, because the human physiology, we had done a course on that before, and as you know, is very calculative. So it only wants to use as much as it should use, right? So why is that? Because why do you want to produce products only up to a certain quantity and no more than that? Because what happens is that the product can stimulate a biochemical pathway that is needed in certain times. For example, if the product is present in a certain specific quantity, it stimulates a certain biochemical pathway. If it exceeds that quantity or lesser than that, it can stimulate some other biochemical pathway which is maybe undesired. Okay, so that is reason number one. Reason number two is that the products typically are biologically active over a very small concentration range. And some of you who have studied or are interested or have learned anything on drug delivery would know that when we deliver drugs, for example, your doctor tells you to take the medicine at a certain quantity, not more, not less, right? Why is that? Because if it's less than that particular quantity, then the drug is not effective. If it's more than that particular quantity, it's no good either, because it can start to have side reactions. So what happens is, and if we do, if we get any time to do one lecture on drug delivery in this course, you will see that the drugs are typically active within a very small region or narrow zone on concentration, and same it is with enzymes. Enzymes are active within a small narrow zone, and you have to regulate the enzyme such that it remains within that particular zone. So if the body is producing more of enzyme, it's no good either. If it's producing less, it's no good either. So you want to maintain it such that it's within that particular zone. And the third reason is a very thermodynamic reason, as you can see, is that the excess, if you produce excess enzymes, what will happen? You'll generate excess products, right? And excess products may require too much energy. First, too much energy for generation, right? Whatever is the amount of enzyme, if you use excess enzyme, you'll form excess products, and each of these mole of excess product would need to cross the threshold of energy. So in the process, the body is going to use up more energy, right, than it should. And as I said, the physiological body is a very miser, very calculative entity. So it tries to always minimize the amount of energy it spends. So think of yourself, given that you can sit, you would not stand. Given that you can sleep, you would not sit, right? So it's as simple as that. So your body would like to use energy as miserly as possible. As a result, it would never like to generate products that it is not going to use, because it's going to waste energy, A. And the other option is that if you generate more product, and that is one of the things that I said at the start of this lecture, it can interfere with other biochemical pathways. It can trigger off other biochemical pathways which are not desired. So you don't want any of these. So to do this, you regulate. Okay, and the way you regulate is essentially by using inhibition. So the question is, how does one inhibit? So one inhibits by regulating the substrate, products, or other molecules that work or interact with the enzymes. What does this mean? The enzyme is, and I gave you a clue to this a little before also, not in today's lecture, one of the earlier lectures, is that an enzyme is specific and it's supposed to interact or react with a certain substrate, right? Now, if you can mimic another substance or another substrate which resembles the stereochemistry of which resembles that of the substrate that the enzyme is specific towards, then the enzyme will deceptively, you kind of deceive the enzyme to start to interact with that substrate, right. So that is the way you do that. There are ways you can use a product also to inhibit, and we'll come to that in the if not in this lecture, maybe in the next lecture. So let's try to see what does inhibition lead to. Inhibition, what does regulation lead to? Regulation leads to inhibition. It could be an intrinsic inhibition or an extrinsic inhibition, that is, you inhibit intrinsically or extrinsically from outside. It leads to activation or lowering the activation energy, the amount of energy. We talked about these things, the amount of energy that you use can lower that. Now, what are the types of inhibition? So, just for your record, these are the 4 different rather types of inhibition. So, the first type of inhibition is known as competitive inhibition. The second type is split up into 2. It's called non-competitive and uncompetitive, and the third one is substrate inhibition. So, at this point, I'm going to discuss all of this in great detail, but let me test your intuition a little bit. What do you think would be a competitive inhibition? Just intuitively, I'm not even asking about the reactions. I'll give you the reactions in a minute, but intuitively, what do you think would be a competitive inhibition?
We'll use a substrate which has the same stereochemistry as the substrate.
Yeah, then what will happen?
Will compete with the same enzyme.
Will compete with the same enzyme. That's right. Yeah, that's competitive inhibition. What would be non-competitive or uncompetitive inhibition? Say non-competitive.
We reduce the activity of the enzyme.
No, not really. What would be a substrate inhibition?
So the amount of substrate provided to interact with the enzyme is less.
No, not really. Any other thoughts on the last two? The first one is correct. What you said about competitive, that's correct. But any other thoughts on what could be non-competitive? Just some guess. I'm going to discuss this in a few minutes, so that's not the question. But just some guess on what could be non-competitive, what could be substrate. In non-competitive, I'll give you a hint. In non-competitive, the enzyme, the inhibitor. So essentially, in the competitive, what happens? Inhibit, as Krishna Pratap said, inhibitor competes with the substrate, okay, for the attention of the enzyme. Okay, so the enzyme goes and reacts with the substrate, and then the inhibitor also will go and react to the substrate parallelly. So the inhibitor competes with the enzyme for the attention, competes with the substrate for the attention of the enzyme. That's competitive inhibition. In non-competitive, what happens? It does not compete directly with the substrate. Okay, it does not compete directly with the substrate. It goes about some roundabout way. For example, what it does, it can bind to the complex that the substrate binds to. It's getting too complicated. I don't want to go into it right this moment. We'll do it in a few minutes. Substrate inhibition is again simple. It is a system, and these are very specific, special cases where it happens. It is a system where the substrate itself, too much of the substrate, you could the other way around actually from what you said, too much of the substrate if you put in, or excess of the substrate if you put in, the substrate itself can inhibit the reaction, the binding. Okay, so these are the 4 different kinds of inhibition that we're going to do in today's lecture and the next day's lecture. So what I'll start with are examples of competitive reactions. So there are 2 kinds of competitive reactions. One is called competitive parallel, and the other one is called competitive consecutive. Okay, so let's assume that A and B are your feed and S is your desired product. Now, why I did put it this way is I want you to tell me what would be a competitive parallel reaction to start with. You have studied this in your chemical reaction engineering, so I just want you to tell me what would be a competitive parallel reaction.
A gives S and B gives S. Both are parallel the same product.
No, but A and B are reacting. It's a second order reaction. A and B are the substrates, not a single substrate.
A and B goes to P and A plus B goes to S. A plus B goes to P.
A plus?
A plus B goes to P. A plus B goes to S. Both 2 ratios.
Not exactly. Any more thoughts?
A plus B giving 2 products of which one is S.
And You're close. Yeah, you're close. Say A plus B giving two products. Okay, say one is S, or even one product with one is S, and what happens? What did you say, Krishna Pratap? Repeat that one more time.
One reaction A plus B giving P,
Huh.
other reaction A plus B giving S.
Well,
Is that something?
no, not really, but sort of, in a way close, but no, not really. One reaction is A plus B giving P, and the other reaction is either A or B, one of these reactants reacting with something else, not A.
Product of other reaction.
Some other reaction, some other reaction that's a product, some of the substrate that's in the system, or some other product of some other reaction that's in the system, reacting with that to form SA. Okay, so this is how it looks like. So A plus B giving P, okay, P plus Q or P, doesn't matter, and then B reacts simultaneously with some other reactant C which is present in the system to generate S, and S is your desired product. Now what is interesting about this? What is interesting is if you look at the case 1 and case 2, right, A and B are fed in equimolar quantities, as I've written there clearly. A and B are fed in equimolar quantities, right. What is interesting is, think about this, K2 is let's talk of case 1 first, which is easier. Case 2 is first, which is easier, which is K1 is much greater than K2. The first reaction is much faster than the second reaction. So what will happen? Because A and B are fed uniformly and are fed in the ratio of 1:1, what will happen? Very simple, yeah. All of B will react with A because the first reaction is much faster than the second one. So all of B will react with A to form P, and no S is formed. So S is our desired product, which is not going to be formed. In the second case, okay, which is case 1 written over here, is K2. The second reaction is much faster than the first one, in which case A would not get a chance to react with B, and C would react with B to produce my S, which is the desired product, right. So if S is my desired product, what I would really like is, I would really like my second reaction to be much faster than the first one, but well, the world doesn't run the way I want it to, right. And in most cases what happens, these are diazotization, these are ionic reactions. These ionic reactions, many of the ionic reactions come under this category, and what happens is that the first reaction is actually faster than the second one. Okay, so many cases it happens. So I give you a little quiz question here. Tell me, as an engineer, and you have all studied reaction engineering, some very basic reaction engineering principle. I'm feeding A and B uniformly, okay, uniformly in a, say, a continuous stirred tank reactor, and A and B are fed in the ratio of 1:1, and the first reaction is much faster than the second one, which means that no S is going to be produced, but I want my S because that's my desired product. So what should I do?
We can vary the flow rates.
Very no. I already said that A and B are given as the ratio of 1:1. So if I could vary that, then I'm in business, right? What I'll do is that I realize that B is reacting very fast, and I'm going to change the ratio, feeding ratio of B is to 1 A, which I'm not allowed to do. I'm already feeding in 1:1 ratio, and S is my increase the
Concentration of P.
how will that help? P is a product. It's a
We can use inhibitors.
We can use
It
inverse.
can combine with A. We can use any reactant that can combine with A, so that it will combine.
that's a reaction way of doing it, reaction engineering way of doing. What could be a very simple way? Sometimes the simple solutions escape you when you're thinking of something too complicated. There is a simple way.
Residence time is very low.
Making
Residence time very low.
that still wouldn't help, because see, you have studied this in reaction engineering. What will happen is it will produce only in the ratio of S is to P. The yield of S is to yield of P is going to be in the ratio of K2 is to K1. It doesn't matter, independent of the residence time. Yes, Pallavi, what's going to happen? No clue. What should you do? Very simple engineering solution is there. What you should do is, instead of fiddling around with reactions, what he said is a possibility that you introduce another reaction which is going to react with A. That's an interesting way of doing it. But if you don't, that is Yeah, but B is still the limiting reactant, it won't help. You can put as much C as you want, you can flood your reactor with C, but B is still your limiting reactant, so it's going to be dependent on B. So, so yes, one of the things you said that is possible, introduce an inhibitor which is going to react with A, but that's not the only solution. There is an easier solution, which is that very simple, you'll bite your tongue if I tell you, which is that slow down the stirring rate. Just simply slow down the stirring rate. Okay, so you're doing it in a CSTR, continuous stirred tank reactor, and you're stirring at a particular RPM. Simply slow down your stirring rate. Okay, decrease your stirring rate a lot. So if you're stirring at say 300 RPM, you stir at say 50 or 20, and so I gave you the answer. So my question to you is that explain.
It's a mixing. Stirring is mixing. When to this desired product formation for that C and then B and C is.
No, what is just say in keywords? What is going to happen?
The active site means like B is
no. What is the phenomena? What is the phenomena that is going to come in?
dispersion.
Not dispersion. Yes. So you are in the close to the answer, but
It's a mixing coefficient actually.
no. What is the phenomena? What is going to happen? I don't want coefficients and all that. What is going to happen? What is the phenomena that will kick in? So this is a simple reaction happening. A new phenomena will kick in once I start to do that. Once I start reducing the stirring rate, what is that phenomena? What is going to happen is there will be transport limitations or mixing limitations in the system. See, right now there are no mixing or transport limitations in the system. So what is happening is that whatever is the reaction rate, that is going to be the final yield is going to depend on K1 and K2. But as soon as you increase your mixing limitations, so slow down your mixing rates, then you are going to introduce mass transfer resistances in the system. Okay, so your reaction rate is no longer going to be the reaction rate that was prevalent. Now K, you have to figure this out. It's a very straightforward thing, and deals with the basics of reaction engineering, which are which are something that we are interested in this class, which is that when you introduce mass transfer limitations in the system and there are reactions going on, which reaction does it hurt? The faster reaction. Okay, because the faster reaction is not inhibited by mass transfer, and when you introduce mass transfer resistance in the system, it's a faster reaction that it hurts. So what will happen is that because K1 is much faster than K2, it is going to slow down the K1, the first reaction, and it's going to have hardly any effect on the second reaction, because see, what mass transfer does is it sets an upper limit on the rate of reaction. So if your rate is already much lower below that upper limit, it doesn't make any difference. But if it's above that upper limit, then mass transfer will pull it down. Right? Is it clear, everybody? Okay. So this is the trick to do. So introduce mixing limitations in the system, and as a result of which, what will happen is that the first reaction would be slowed down, while the second reaction will remain as it is, and the relative yield will go up of S. Okay, and these are the reason I went into such details about this, because these are things that we need to understand. Let's see. So the second reaction is competitive consecutive type reaction. Here what you do is use A and B as feed, 1:1 feed, and again an S is a desired product. The difference, as you see over here, that A plus B giving P plus Q, and it's a product that reacts. If you compare the first one, the second one, what's the difference? In the first one, it's some other reactant or some other substrate or some other product from some other reaction coming and reacting with B, whereas in this reaction it is not that, it is a product of the first reaction which reacts with the second reaction with B in the second reaction, which means that this is essentially competitive consecutive, or it's also known as competitive series. So the first reaction is parallel and the second reaction is in series. Okay, you cannot pull off a lot of tricks in this case really, but again you can still do the same thing. So again, what happens is if K1 is much faster than K2, as I said, then what happens is all the what B is, yeah, all the B is consumed in reaction A, reaction 1, and there is no B left that can react with Q to form the product. And again you can pull out the same trick, right. You can use a stirring limitation or mixing limitations to and introduce that. As a result, the first one, what will happen is the first one will not be complete, and the second one will be allowed to happen. What I want you to do is, when you go back home, is that for this case, competitive consecutive, for example, is a little easier. There is an asymptote. See, can you keep on increasing mixing limitations, and can you do that? Yes, you can, but there is an asymptote. Why is there an asymptote? Because it is no longer governed by reaction. When you introduce mixing limitations in the system, the yield is dictated by the mass transfer resistance in the system, and what I want you to do is to figure out what the yield of S is going to be, okay, under mass transfer limitations. Because you have been taught in reaction engineering, the yield of S in the absence of mass transfer limitations you can only get in terms of K1 and K2, right. What I want you to do is, in the presence of mass transfer limitations, what is going to be the yield of S, right. Figured out the question? What is going to be the yield of S if you introduce mass transfer limitations such that K1 is much greater than K2. In other words, I want you to do this case particularly, K1 over K2 goes to infinity. So, K1 is instantaneous, K2 is reasonably slow. So, we introduce mass transfer limitations, as a result of which the first reaction will be hurt, the second reaction is not going to be hurt, right. And I want you to figure out that what is the amount of S that is formed under those conditions. So, so if this goes to infinity and introduce mass transfer limitations, S is formed. Okay. In the absence of mass transfer limitations, no S is formed. In the presence of mass transfer limitation, S is formed, and I want you to figure out what that amount is. Okay. So, now what we will do is we will go on to competitive inhibition, and I will try and explain what it is. Because I gave you the background in terms of competitive consecutive and competitive parallel reactions, this will be very easy for you to understand. So, I just wanted to give you a very familiar background in reaction engineering, and then you can map that to what we are doing over here. So, this is a competitive inhibition, slightly more complicated than the thing that we did last time, but still very straightforward. So, the first reaction, as you see, is the same as what we had done before, which is E plus S reversible giving ES, which then irreversibly breaks down into the enzyme and generates the product as well, right. The second reaction is the one that makes a difference. As I told you, these are competitive. What kind is this? Competitive what? Which kind of competitive? Competitive inhibition, of course, but what kind of competitive? We did two kinds of competitive just now. Which one is this? Just look at it and tell me. You don't have to go back to the notes. Huh? Oh, I'm sorry. Yeah. Okay. So, the first one is yeah, E plus S giving ES, which breaks down to enzyme and the product, and the second one is E plus I giving EI. Okay. So, all I am asking is this a competitive inhibition? So, which kind of competitive is it? Competitive parallel. Okay, very straightforward. Why? Because S and I are acting parallel to each other in interacting with the enzyme. So, as I said, put it in a more different way, is that both the substrate and the inhibitor are parallelly competing for the attention of the enzyme. Okay. So, this is a nice picture here. So, this is so this is the substrate, and this is the substrate S, and then this is the inhibitor. What you see there, what is interesting in the structure of the substrate, if you can see that the blue one is the substrate, the red one is the inhibitor. What is interesting is that the similar stereochemistry, yes, similar structure of that. So, this is a lock and key mechanism, right. The enzyme and the substrates are always specific to each other, and there is a lock and key mechanism. So, there is the enzyme, this is active site of the enzyme, okay, and this fits in fits into the substrate. Okay. So, the enzyme and the substrate and the inhibitor they have similar structure. As a result, both of them can fit in. So, they both are competing. So, this picture shows that they are both competing to occupy that slot in the enzyme, and either the inhibitor can occupy that spot or the substrate can occupy that spot. As a result, then inhibitor enzyme complex could be formed, or a substrate enzyme complex could be formed. Okay. Is it clear? Okay. So, now what we will do is, like we did in the last class, we will do the derivation and try to figure out what the rate is, because at the end of the day what we are interested in is the rate. the questions that we have to ask ourselves are is this a Michaelis-Menten kinetics after inhibition? It may or may not be, because sometimes kinds of inhibition are not Michaelis-Menten. It deviates from the Michaelis-Menten structure. Some kinds of inhibition retain the Michaelis-Menten form. So question A is that we have to discuss that is it a Michaelis-Menten form. If it is a Michaelis-Menten form, what are reduced? Is the maximum reaction rate reduced, or the Km, the Michaelis constant, that is reduced? So will one of you tell me at this point, from what we did in the last two classes, what does it mean? What does the maximum reaction rate being reduced imply? What does the Michaelis constant being reduced imply? If you just quickly, if you want to go back to your notes, you can check any of the plots that we did, and you'll see what I'm trying to ask. It's a very straightforward question, but we need to understand that. What does the maximum reaction rate imply? It implies that whatever is the maximum reaction rate attainable, and if that is reduced, that is a sort of inhibition. See, I now want you to look at why I'm raising this question at this point of time is that I now want you to look at the whole concept of maximum reaction rate and the concept of Michaelis and the Michaelis constant in the light of inhibition. Okay, till now you just looked at it as constants of your reaction, but now I want you to look at it in the light of inhibition. So in the light of inhibition, what does maximum reaction rate being reduced means, or increased or reduced means? As that the maximum attainable reaction rate is reduced means it's being inhibited in a way, right? Then what does the Michaelis constant Km imply? It gives you, in the plot, it gives you what? The yeah, but in your plot, just to answer my question simply, in your plot, what does the Michaelis constant correspond to? The maximum reaction rate corresponds to a line parallel to the x-axis, right? Okay, so which is one of the limits, saturation limits? Which limit is the zero? Which order kinetics? Huh? It's which order is that? The maximum reaction rate? It's the zeroth order asymptote, right? And the small cs is the first order asymptote. So what does the Michaelis constant correspond to in your plot? You have your notes. What it corresponds to is a it gives you the slope in a way, right? Once you fix your maximum reaction rate, your slope is km over R max, right? So if once you fix the maximum reaction rate, it will give you the slope, and therefore it will give you the reaction rate in case of the first order kinetics. So how fast that is the first order is, right? So if you can reduce, now again coming back to that in the light of inhibition, so if you can reduce your Michaelis constant Km, what can you reduce? What? Can you inhibit? My question, to put it more simply, people are not getting it. Maybe it's too early in the morning. So, can you inhibit the reaction by increasing or decreasing the Michaelis constant? Okay. So you will see that, yes, but the answer is that it is possible. Okay. So what I want you to do is first, so we'll go through this in the next half hour or whatever we have. We'll go through the derivation of competitive inhibition, and I want you to actually work it out with pen and paper, because that's the only way you can learn it. So the first assumption that we make is that let's go back to the equations again to jog up your memory. So what is happening? Look at the first reaction. This is what we did in the last class, right? The simple case where the enzyme reacts with the substrate to produce a complex ES, which then breaks down into the enzyme and the product. What was the major assumption that was there? That ES is a complex which is short-lived, and as a result it breaks down very quickly, and therefore we can assume a quasi steady state or a pseudo steady state approximation on ES, right? Which means that the rate of accumulation of ES, in simple mathematical terms, the rate of accumulation of ES is 0. So ddt of CES is 0. That was what we had assumed. Then we had already also discussed and gone into great detail to try and quantify under what conditions this assumption is valid or not. And right, we figured out that under certain ratios of K2 and K1 this is valid. Okay, so here what we do is we assume that yes, this is valid. Okay, so we assume that your CS is ddt of CES is 0. So ddt of CES is 0. So this is the first assumption that we make, and ddt of CES is given by this number. Okay, Ashwin, I want you to put your pen to paper and start writing this. So ddt of CES is 0. So your ddt of CES equals this. Okay, so which is the forward reaction minus the backward reaction and minus the formation of the product. So CES is formed from the forward reaction, again dissociates in backward reaction, and then the product is also formed from the complex. Okay, so once this is 0, what you can do is you can get in terms of the ratio of in terms of the substrate and the enzyme CE and CS. Why are we trying to do that? We discussed this in the last class. Why are you trying to do that? Parameters, and not just that, to be able to express them in terms of measurable quantities, right? To be able to express them in terms of measurable quantities, which are CE naught, which is the initial concentration of the enzyme, and CS, which is the concentration of the substrate. Okay, so that's the whole idea. Now once we make the steady-state assumption, we can do this, and then we can express our CE and CS in terms of Km, which is again a function of the K1 minus 1 and K2 and K1 all three. And this we discussed before, that this is precisely the answer to this is the answer that you gave first, which is that we use Km, the Michaelis constant, to reduce the number of parameters. We express it in terms of CE and CS so that to express in terms of measurable quantities. Okay, what should be the next step? What do you think? The constraint equation, yeah, that's what is called the constraint equation. Yeah, we'll do that, but next step that we are using here is that the equilibrium relation. So reaction 2 that was there, if I need to go back, I'll go back here. This reaction, the second reaction, that is enzyme and the inhibitor reaction, attains equilibrium, which means that you can straight away get a relationship between EI and I. Okay, so this is what you do. So you can straight away get a relationship between this, and Ki is known as the equilibrium constant for the inhibitor, which is the K minus I over Ki. K minus I being the backward reaction rate and Ki being the forward reaction rate. Okay. Because see, the complexity that we have over here is that what is added complexity in terms of us solving the equation as compared to what we did in the last lecture? You have what is the added complexity in terms of actually solving this equation as compared to which complex? Yeah, EI, right. So that's the added complexity we have. That is, we need to eliminate one more complex. Last time we had just one complex ES. This time we have two complexes, ES and EI, and we need to eliminate that. So the first step we use towards that process is given in equation 4, which is to express my EI in terms of CE and CI and the inhibitor rate constant or the equilibrium constant. Okay, now with the constraint equation. Now I'll give you the constraint equation in a few seconds, but I want you to write it down on your own and tell me what it's going to be. So CE naught is my initial concentration of the enzyme, and what should that be equal to? Yes, Pallavi? CEI. Then you can express your CES and CEI in terms of other quantities, because both these reactions are assumed to attain equilibrium, right? So you see on the screen what I intended. So CE naught equals CES plus CEI plus CEI. So those of you who were not there in the last class, for you, so the constraint equation is essentially the equation where you balance the enzyme present in all different forms. So initially it's a mass balance equation in a way to think of. So initially if I put CE naught amount of enzyme into the system, it has to be present in all the different forms that the enzyme is present, which could be complexes. We have two complexes here, CES and CEI, or the enzyme in the free form. So it has to be out of these, between these three forms it has to be there, it cannot vanish anywhere. So, and because these are isothermal reactions also. So so CES, because you know, I can assume, so how do we get CES equals CE times CS over Km from the I just showed here before, right, from this, okay, the quasi steady state assumption, and this one is equation 4 given on top, and CE as it is. So what we have been able to achieve, we have been able to achieve eliminate both the complexes out of the system and express everything in terms of CE and CS and CI. Okay. So what is, we still have one more step to go. What is that step? What do we need to do? No, eliminate what? One more elimination is left. C? CI we have already eliminated. Look at equation 5 on the screen. CI we have already eliminated. What else is left to eliminate now? What else is left to eliminate? We did this in the last class. C? CE, right? Yeah, CE we have to eliminate, because CE again is a quantity that we cannot measure at any points of all points of time. So we need to measure in terms of CE naught, the initial amount of the enzyme that we gave in, and this is what we do. So we take we invert this relationship. So CE we express in terms of CE naught, CS and CI, right? Is it right? Okay. So CES is now, you know, if I, so I have expressed my CE. So if you want to write down, you can write down equation 6. I'll give you a few more seconds to do that. Done. So CE is now expressed in terms of CE naught, CS and CI. So once I have done that, my CES equals CE times CS times over Km. Okay, this is from the quasi steady state I got. Now I can replace my CE by CE naught and that function over here. So what I get is CE naught CS divided by Km into 1 plus CI over Ki plus CS. Why am I expressing CES in terms of other quantities? Because very simple, because the reaction, right. So because the rate of product formation is given by K2 times CES. Okay, because if you remember, the rate of product formation was the irreversible reaction that led to P, formation of P. Okay, right, Lisa? Yeah. So that was simply equals K2 times CES. Now we have been able to express CES in terms of known quantities such as CE naught and CS and CI and everything, and so we have been able to express this, and this is the way we put it. So once we've put it, then from analogy, what you can see, this retains the Michaelis-Menten form, right? Because this was one of the questions that we thought was important, right? I said we have to answer various questions, but the first one of that is the fact that whether it retains the Michaelis-Menten form or not. And what we figured out is that yes, this type of inhibition, the competitive inhibition, retains the Michaelis-Menten form, which is that it can be expressed in terms of, the rate can be expressed in terms of Rmax times the substrate concentration divided by a constant plus the substrate concentration. Okay. So by analogy, what would be your Rmax and your Km and so on? What is Rmax? Rmax remains the same, which is K2 into C naught, right? Rmax is your K2 into C naught, and I discussed this in the last class. So who will tell me that why is Rmax equals, intuitively, why is Rmax equals K2 into C naught? Yeah, if all the enzyme actually reacted and formed product, then the reaction rate would simply be K2 into C naught into CS. So yeah, K2 into C naught. So your Rmax equals K2 into C naught, and Km hat is this quantity, right? So which means what? That your Rmax is still the same in competitive inhibition, but your Km has changed. Okay, and what I think you said this before at the end of the class, that once your Km increases, then you can inhibit, right? So that was your prediction, and it turns out that is correct. Once Km increases, you can inhibit. And is Km going to increase here or decrease? Is going to increase very clearly, because Ci and Ki both are greater than 0. So therefore Km hat is greater than Km. Okay, so we'll be able to inhibit. So I'll show you a plot here. So okay, so I'm not sure if you can see the plot properly, but these are let me run it for you. So these are the rates in micromolar per second on the left, and Cs, the y-axis is micromolar per second, the x-axis is the concentration of the substrate in micromolar. And what are these Ci's on top that you see? These are the inhibitor concentrations. So the top graph is for no inhibitor at all, the second one is for inhibitor equals 20 micromolar, the third one is for inhibitor equals 50 micromolar. Okay, so this is without inhibition. You see that it is whatever is the rate. So if you introduce a certain amount of inhibition, it goes down, and it goes down further as you keep increasing the rate of inhibition. And these are real, actually, numbers from experiments, and the Rmax that you get over here is around 25 micromolar per second. This m should be a big M actually, and Km, the Michaelis constant, is around 5 micromolar, and Ki, the inhibitor rate constant, is around 10 micromolar. Okay, so the first thing that we see is that as the slope goes to 0, okay, and this we have discussed in the last class as well, this is the first asymptote, the first order asymptote, right? So as the slope goes to as the Cs goes to 0, the slope goes to Rmax over Km, right? So though your Rmax remains the same, your Km, because your Km changes, so the slope changes. Okay, and what you will see, so the Rmax over here remains the same, and what you will see is that what is not obvious from the graph, but what we'll actually see is that if you go on for a very long time, they will all merge. Okay, all these graphs will merge. So as a result, the Rmax will actually not change, but these are over a certain period of time. But because the slope changes at the beginning, right, because slope is Rmax over Km, because Km changes, the slope changes, so they will attain that asymptote at a very different rate. Is it clear? Though the asymptote could be the same, but because your initial slope is very different from each other, because your Km is very different, they will attain that asymptote. The dynamics of attainment of that asymptote are going to be very different, and as Km decreases, the slope increases, right? So this is understood, I guess. So so is there any question on competitive inhibition at this point of time? If there is, you can ask, and then otherwise I'll go and do a little bit of uncompetitive inhibition. No questions? Okay. So before we start with uncompetitive inhibition, let me ask you, what are your thoughts on so you had not been able to tell me what uncompetitive inhibition is at that point of time. So I gave you a hint that what it could be. Now after having done competitive inhibition, do you want to take another try at that? What do you think would be uncompetitive inhibition? I said that before, but if you want, I'll give you the answer. So so what happens is the inhibitor in uncompetitive inhibition, instead of binding to the active sites in the enzyme, the inhibitor goes and binds in other sites of the enzyme. Okay, it goes and binds in other sites of the enzyme. It doesn't bind necessarily to the active site. It goes and binds in other sites. And you might ask that, well, how does it hurt? The reason is it forms an altogether different complex. That is how it hurts. Okay, you might ask that, well, if it binds to the active site, doesn't bind to the active site, then how does it matter? Well, the reason why it matters is this, because it will form an altogether different complex, which can give rise to different sets of products altogether. So this is substrate, and as you see, what is the difference now? The stereochemistry of the inhibitor and the substrate are different, so they do not go and fit to the same slot as before. Earlier they were going and fitting to the same slot. So how do you, if I ask you this question, how do you ensure that a certain kind of inhibition is competitive and another kind of inhibition is uncompetitive? By manipulating the manipulating the structure of the stereochemistry, or the structure of the inhibitor, right. So, if you want to have a competitive inhibition, then you mimic the structure of the substrate. If you want to have a different kind of inhibition, for example uncompetitive, then you make sure that it goes and binds with the enzyme, but it does not have the same structure as the complex. So, these are some of the, when you do these kind of biochemical interactions and experiments, so these are the kind of things that you might want to manipulate with. So, this is what happens. So, the substrate has a certain structure, the inhibitor has a different structure over here, as you see, and this will go and fit to this slot, and this will go and fit to this slot. Okay. So, so let's go and understand this. So, what will happen is that so some of the inhibitor that you will have will go and react with the substrate bound enzyme. Okay. So, this substrate is allowed to go and bind to the enzyme always, right. Why am I saying so? Because the substrate typically is present in what kind of quantities? Very less. No, abundant rather. The substrate is present in abundant quantities, the enzyme is present in minute quantities. The substrate is always typically present in abundant quantities, you know how much substrate you waste in the lab. So, so the substrate is present in abundant quantities. So, as a result of which the substrate is always, so if the enzyme is present in small quantities, the substrate is always going to bind to the enzyme. The inhibitor also is present in small quantities, remember. So, some of the inhibitor will go and react or bind to some of the substrate bound compound. Okay. So, that is that clear, the mechanism? Okay. So, now we can go to the reactions, because it otherwise does not make sense to go into the reaction unless the mechanism is physically clear to you. So, as the uncompetitive inhibition, and that is why it is called uncompetitive. So, both are not competing for the active site. Earlier what was happening was both the substrate and the enzyme, the substrate and the inhibitor, they were competing for the active site. Here both are not competing for the active site. As a result, that is why the name nomenclature, and if I tell you, this is the best way to remember it. So, that is why it is called uncompetitive inhibition. So, it does not directly block the active sites of the enzyme, but interacts with enzyme bound substrate on another sites. Okay, reducing the reaction rate. So, this is the equation that you get. So, first equation remains as it is. Okay. Earlier what was happening, the second equation, so just just remember how these mechanisms work. So, in first equation, equation 1 is like it is always there. So, in presence of inhibitor, in absence of inhibitor, it is there. So, that is a E plus S giving ES, and which generates E plus P, P being the product. The second reaction, last time in competitive inhibition, it was what, E plus I giving EI, which means that it was competing with the active site. In this case, it is not competing with the active site, but it is going and binding to the complex, the enzyme substrate complex, forming some other compound ESI, which is not leading to products. So, essentially it is not blocking the active site itself, but it is generating some other complex which does not lead to product formation. Okay. So, this is a picture of the thing. So, this is another picture of the thing. So, this is the substrate is given here and the enzyme by a triangle, and this goes and binds. So, the substrate goes and binds. So, typically much of it some of it is in this form, but some of it, this ES that is formed, again binds with the inhibitor to form the ESI. Okay. So, what I am going to do now is we are going to start working on the derivations for the next few minutes, and I'll give you some hints, but I want you to work on it. So, let me ask you first. That first assumption is that reaction 2 that you had over here is this is going to attain equilibrium, right? So, if you want to go back to your calculations, what I suggest is that the calculations for equation 1 remain the same. So, you do not need to redo those calculations. What you need to redo is this calculation for the reaction 2. So, I would like you to do that. So, the first assumption here is that reaction 2 is in equilibrium. Okay. So, what would that lead to? A relationship between your what does that lead to? If you assume that the first reaction is in equilibrium, what do you get? second reaction is in equilibrium, yeah. So what will you get?
Equilibrium constant Ki equal to CESI plus CES into CES.
Right. So this is what you will get. So CESI equals CES over CI over Ki, where Ki is the equilibrium constant for the inhibitor, the backward reaction over the forward reaction. Fine. Okay. Next, what will you do? The which assumption next? Yeah, the quasi steady state you can use. Then you will get, that will help you get the relationship between CE, CS and CES, right? So it's the same thing that we had before. Okay. Slightly different maybe. Okay. What we'll do next is a constraint equation. We'll come to the quasi steady state a little later, just after this. So the next thing that I want to ask you is what is the constraint equation going to be? Similar as before, slightly different, which is CE naught equals CE plus CS, CE plus CES plus CESI, right? As simple as that. Okay. Now the quasi steady state assumption. So the quasi steady state assumption is, and I wanted you to write it, but because we don't have a lot of time today, I just want to make sure that you understand that it has to be written in this form. Just look at what is on the screen and explain to me why these. So the difference that you have over here is that, okay, and just explain to me what is the difference between the quasi steady state assumption here. I'm showing you this and the quasi steady state assumption. Where is that? Yeah, here. See, this has three terms, the quasi steady state assumption, and I want you to understand this very clearly. So this has three terms, the quasi steady state assumption, right? Whereas the one in the next that I showed, it has 5 terms. Why is that? Yes, yeah, that's the reason, because ES is also taking part in the reaction as a result of which. So ES is taking part in the second reaction as well. In the first earlier case, in competitive, ES was not taking part in reaction 2, so it was only there in reaction 1, but here ES is taking part in reaction 2 as well, so it's a part of that. But then I cancel these two. Why do I cancel those two? Yeah, because of equilibrium. So the reason I want you to understand this is that, see, there is a difference between steady state and equilibrium, and many times I find the students confuse this up and they assume that equilibrium equals steady state. There are times when equilibrium equals steady state, but there are many times when equilibrium doesn't equal steady state. So in this case, for example, you have the equilibrium for this reaction. So equilibrium relates to a particular what? Fill in the blanks. Equilibrium relates to, when I talk of equilibrium, I mean equilibrium of a no, in terms of reaction. If I say that if there are reactions happening in the system, when I say there is an equilibrium, I speak of in terms of an equilibrium of a what? Of a particular reaction. When I speak of steady state, I speak of steady state of a particular species. Yeah, that is the fundamental difference between a steady state and an equilibrium, and you have to get this very, very clear in your heads. So when I speak of equilibrium, equilibrium is for a particular reaction, whereas steady state is for a particular species. So here, if you look at it, this reaction has attained equilibrium doesn't mean that ES has attained steady state, right? ES actually doesn't attain steady state at all. We assume that it attains steady state for the simplicity of our calculations and for certain conditions which we are able to justify, but it doesn't attain steady state in general. So this is what we have. So you see, and this is what we have. So these two will cancel out with each other, and k minus this, because of equilibrium, these two terms will cancel out, and then you will have a relationship which is again similar to what we had. But make no mistake, the derivation is not the same. Okay. So let's then go to, I think we don't have a lot of time. I think probably we won't be able to finish the derivations today. What I'll do is we won't do the derivations, and just for the next couple of minutes we have, I'll just summarize quickly what we did. So in this lecture what we essentially did was we started talking about inhibition and why we need inhibition, which was to regulate the product quantity of product that is formed. And the reason we regulate the quantity of product that is formed is that we want to stimulate a certain biochemical pathway and not stimulate other biochemical pathways, and because the product is typically active over a small range in concentration B. And third reason is that if you generate a lot of product, it will accumulate and a lot of more energy will be formed. So so we understand why we need to regulate, and the way we regulate is by using inhibition. So in most cases we introduce an external inhibition, and it could be intrinsic as well. So inhibition here, it says, could be intrinsic as well as extrinsic. So in most cases we introduce an external inhibition, and there are 4 different kinds of inhibition that we'll study in these lectures: competitive, non-competitive, uncompetitive, and substrate. Out of these 4, the first 3 are extrinsic inhibition, which means that you introduce an inhibitor, and the last one is an intrinsic inhibition, which means that the system itself inhibits. Okay, these are inhibitory systems, and they're very interesting systems. They have their dynamics, and we won't be able to study those dynamics in this class, but they're pretty interesting. So today we did the competitive inhibition, and we finished off competitive inhibition. We showed that in competitive inhibition the maximum reaction rate remains the same, while as the Michaelis constant changes, as a result of which the slope changes and the reaction is inhibited, the reaction rate is inhibited. We are working on the non-competitive, and we'll continue that in the next lecture. So that is all for today. Thank you. So, and I'll meet you in the next lecture.